All right, we just found out that integrals and derivatives are the opposite sorts of things. If I was going to be fancy about it, I would say that integrals and derivatives are inverse processes. So integrals undo derivatives, derivatives undo integrals. Now, the payoff to this means that every single thing we learned about derivatives back in Calculus 1, we can take any of those formulas and rewrite them into a formula for integrals instead. Let's take some easy ones just to start off this idea. So here are some derivative rules. Because I know the derivative of the cosine of x is equal to minus the sine of x, and because I know integrals undo derivatives, I can use this rule to say that the integral of minus the sine of x dx must be equal to the cosine of x plus some constant. So anytime I'm doing an indefinite integral like this, I will have a constant of integration. Derivatives always have us losing information, so we have to have this constant here. And in a problem for the real world, we might have to solve for the value of that constant. But for right now in this lecture, it's just an indefinite integral, so I'm going to leave that plus c. I was able to get this formula without any calculation at all, just because of my prior knowledge about the derivative of the cosine function. Let's take someone that's a little bit more complicated. Let's have this polynomial. So here I want the derivative in the variable x of the function 1 plus x squared, that whole quantity raised to the third power. Now, we could multiply that out, but I don't want to, so we won't. Instead, let's use the chain rule formula. The chain rule formula says, do the derivative of your outside function first, then multiply by the derivative of the inside function. So my outside function is the cubing function. I bring down my 3 and I make the exponent 2. My inside function stays the same. My 1 plus x squared stays the same. But I have to multiply on the outside by the derivative of 1 plus x squared, which is just 2 times x. For this slide, I've gone ahead and rearranged this. I left out the scratch work, and I wrote my derivative as 6 times the quantity 1 plus x squared, which is then squared again, times x. So just a little algebraic manipulation there. And that would be my derivative. This means I can go backwards as well, because this function, the quantity 1 plus x squared, which is then cubed, is an antiderivative for the function 6 times 1 plus x squared, which is then squared, times x. So let me rewrite that as an integral formula instead. If I want to integrate the function 6 times the quantity 1 plus x squared, which is then squared, times x dx, goodness, what a mouthful. Someone should invent a symbolic language that I don't have to say that every time. Moving on. If I want to calculate that integration, I know I'm looking for the indefinite integral, so I just need to give one possible antiderivative and be mindful that there's a plus c on the end. I know automatically from the previous line that the quantity 1 plus x squared, which is then cubed, that'll do just fine. So I can calculate this integral because I knew the derivative rule first. This kind of reasoning is the stuff that makes derivatives very important for this class. So the reasons that I have been reviewing derivatives is so that we can have access to more and more integral formulas, more and more complicated integral formulas. In my next video, I'm going to take this same reasoning and show how U substitution works.